So just one non-example that I forgot to mention. After we proved that every G that has a lattice is unimodular. But there are groups that are not unimodular, and the following is the simplest that I know. The affine translations of the real line. It's maps of the form x goes to ax plus b, where a is non-zero. It's a semi-direct product of the multiplicative group and the additive group of the reals, multiplicative and positive. I don't know, it's the standard notation. And it's not unimodular. And essentially, you can show, you can write the formula for the left Haar measure. That's a way to approach it. So exercise is to check that the following is a Haar measure, just showing it's invariant to left translations. So mu of a equal to the integral over a. We can think about it in living in R2, for example, of 1 over a squared dA dB, where a lives in the first coordinate, and the exercise that this is left invariant Haar measure, and its modular character is given by 1 over absolute value of x. It's interesting to play around using change of variables formula.
So what is x?
X is an element of the... Okay, so let's say maybe R. For the notation we used previously, R is in the affine group.
So what is the absolute value of R?
Oh, sorry. I'm sorry. So each element of the affine group is A comma B. So let's say R1, R2 is an element of the group. So it's given by 1 over R absolute value.
You don't need
It's operator.
which R?
Sorry?
One absolute value?
Why absolute value?
No.
It comes
Which one?
R1, the first,
The A thing.
living in the multiplicative.
And if you already bother to write the absolute value there, maybe you can erase this bigger than zero notation in a definition. Yes.
In the definition. All right. Yeah. Okay.
Okay. Because this is the standard.
All right. So
I mean,
this
if you want to be bigger than zero, then this is the identity component.
yeah. Yeah. Okay. Okay. So just an example I forgot.
This group
It
doesn't have any lattices.
doesn't have any lattices. It's
there-
not unimodular.
Right, so is there a group which has lattices but none of them are co-compact?
None of them. I know. Well, we'll mention hopefully in the future that SLN Z. Well, Lars showed it. Is non-uniform in SLNR with a
You do have co-compact lattices in SLNR.
Okay, so I don't know.
I think yes, but I'm not sure.
Okay, interesting
In
question.
Lie groups, in semi-simple Lie groups, I don't think you can.
No, in
find
semi-simple
They're all
Legos you
in
always have
yes,
both co-compact and non-compact.
So from now on,
There are some crazy soluble groups that you can arrange them, I suppose.
okay. So from now, I will assume that G is second countable, and I would like to introduce the concept of a fundamental domain. So claim, suppose gamma is discrete in G. So then there exists omega or L such that pi restricted to omega to G mod gamma is bijective. So this is what we said, which was a section, but other ways to write this condition down is that equivalently, let's put a bubble, equivalently G is the disjoint union of omega gamma, where gamma runs in big gamma. So the injective property means that this is disjoint, and the surjective means that it covers everything. Alright? So the proof of this, we'll do an outline. First, because gamma is discrete, then there is a neighborhood which isolates the identity element. So there exists U open such that U inverse U intersect gamma is the identity element. This is one of the standard arguments. If you have an open, you can find a symmetric one inside it such that the square is in. What this tells us that on U at least, the projection is injective. Because if we have U gamma equal to U prime gamma, then U inverse U prime is in on one hand in gamma, and on the other hand it's in U inverse U. So we definitely have that U is equal to U prime. So at least on U, pi is injective. And we would like it to be bijective. So let us consider all the translations of U in G. Because G is second countable, you can take a countable subcover. So G is the union of gamma in gamma. No. Sorry. I'm sorry. G is the union from I equals 1 to infinity of Gi U for some Gi. Countable sequence. You just translate U by everything, take a countable subcover from second countability. So now, at least to make it bijective, you need to choose representatives which are not in U. Pi is injective on G1U for similar reasons exactly. The same proof follows. So let's add to G1U. So to G1U, let's add G2U. But remove all the elements that have representatives in G1U. So how do we write it down? So you remove G1U, but not just that, all the gamma translates. You will remove all the representatives of G1U from G2U, it translates, so this will be disjoint, but it will still not cover everything. So you keep doing that. So you keep adding disjointly G3U minus G2U gamma union G1U gamma. Maybe I should, it's not so clear. G2U gamma union G1U gamma. And you can continue doing this. Pi will inductively be injective, and consider omega to be defined as the union on I equals 1 n to infinity of G and U minus the union of all the previous translations of the previous elements. So Gi U gamma. So the argument is that if you can do this formally, but the inductive argument tells you that this is injective, pi is injective on omega, and it covers everything because that we started with this cover. You can do this formally, but we're strict on time, and the proof is not interesting at all, I think. I mean, just playing with set inclusions and there exists a gamma, blah blah blah. It's not interesting.
I think you said it all. No?
I did say, but didn't try it, maybe. But so this is omega, and omega is Borel. You can see from this union differences, it's a Borel subset. Okay, so what happens in this claim? Gamma is discrete. What happens?
On the point that it's Borel, right? Because always you can, like with axiom of choice, just take a bunch of representatives.
Yeah.
But the idea is that it's a nice set.
Yeah, yeah, it's relatively nice. I think that in some connected Lie group, I don't remember the conditions, you can choose it to be also connected and have nice properties, but I don't remember exactly. With the theorem of Hopf-Lee now, I think. Something. In any case, some claim about, the most important thing is that omega is called the fundamental domain. Omega is called the fundamental domain for gamma. Okay, so let's relate it to the cases of lattices with the same assumptions. Gamma, and that the modular function of G restricted to gamma is 1. Gamma is a lattice if and only if the Borel fundamental domain in question is finite measure. Mu of omega is a finite measure. Exists fundamental domain. So now comes the integral formula that we forgot about already. Okay, I can do it here.
So, I mean, this set is unique.
Sorry, again?
I mean, I would get it's not. But the set is unique.
Omega?
Yeah.
Well, all the
You just write it.
left shifts of it is the same. So if you have this, multiply from the left by...
you can choose omega, instead of omega, you can choose omega gamma from some gamma.
Maybe G omega, I would prefer.
G omega.
Think of Z now. So do you know a specific fundamental domain for this lattice?
It's 0, 1.
Yeah, is it unique?
No.
Yeah, and it's also not only translates of omega. You can mix it up, spread it around.
Yeah.
So it's not really unique.
You can choose the GIs in different order.
Okay, so recall the integral formula of repeated integrals. In the case, because gamma is discrete, then the measure is counting measure, and the integral turns into a sum. So it's so let's write it clearly. What does it mean for mu omega to be finite? So mu omega is equal to the integral in G of the indicator function, which is the repeated integral of G mod H, gamma, over the integral of gamma, which is the sum over the elements of gamma in gamma, of the indicator function of omega, G gamma dg. Alright, and what is this? Because omega is a fundamental domain, for all G, there is some translate of G gamma by gamma such that G gamma is in omega. So this is at least one. But the injectivity tells us that there's only one. I'm talking about this sum. For every G in G, some translate of it will give us that it belongs to omega, and it's a unique one. So this is actually identically 1. So this is equal to the integral over G mod H of 1.
Okay, one more time.
Yes, I'll just say that this is equal to nu of G mod, this is gamma, nu of G mod gamma, and this is finite if and only if this is finite. Now let's go back to the equality here. Let's also switch. So take an element in G. So we say that this is equal to 1. Why is that? So G gamma, for all G, in G, there is some gamma in gamma uniquely, such that G gamma is in omega. Alright? So it's always 1. For every G that you chooses, this sum is always 1. Is it confusing or understandable? Any questions? Alright. So more, actually, we said more than that. We said, in this case, any two fundamental domains will have the same measure. Because the calculation was not dependent on the choice of omega. So fundamental domains are important. We had at least we talked in my lecture previous semester of a fundamental domain of SL2Z in the hyperbolic plane, or some variation on SL2R. And what do we want to talk about now? Just a remark that when you have a fundamental domain, this relates to what we started. The remark in the beginning is that when you have a fundamental domain, you can define, essentially, with these assumptions, you can define nu of A to be equal to mu of A, to mu of the inverse image by the projection intersect omega. So if you want to define a measure on G mod gamma, you first pull back by the projection to G, intersect it with the fundamental domain, and measure them. Is G invariant measure on G mod gamma? So
I want to say that if this is new to you and this is kind of theoretical, just think of R and Z and R mod Z, and how do we define the measure on the circle by comparing it to the interval 0, 1, etc. I mean, this is very explicit in examples, and we have various examples, but it could also be discussed in at most general.
So I just want to mention a corollary or an exercise, if you like. Using similar techniques, you can show that any set that injects, any Borel set that injects to G mod gamma its measure is the same when you measure the push and the original one. I will write it down because I said it in a funny way. Suppose S in G, corollary. Suppose S in G is a Borel subset that injects to G mod gamma, then mu of S is equal to nu of pi S. You can show it with similar reasoning if you like. But I will not use it, it seems. Just wanted to mention it. So now returning to the question of when is a lattice uniform, and some condition is given by the following criteria. Suppose G is second countable and gamma is a lattice. So let's see, it's a theorem. Okay. And let Gn in G be a sequence. Then pi of Gn escapes to infinity if and only if there exists a sequence of elements of gamma that are not the identity, such that its conjugate by G goes to 1. So in our case, when G is second countable group, locally compact, topological, then G is metrizable. Then it tells us exactly when G mod gamma is compact. Because having a sequence approaching infinity means that it escapes every compact set, and in particular the quotient will not be compact. So I won't have time to prove it, even though I prepared some outline. I would like to show a corollary.
Maybe if there's I've heard one time Tzafik give a very nice intuition to this. Because if we think about like G, let's say to be a nice simply connected group, and then gamma is a lattice, so from what I talked about last time, when you mod by gamma, you get let's say you get a manifold, or at least something okay. The fundamental group of that will be exactly gamma. Remember, because if gamma acts freely and properly discontinuously on G, it acts in a discrete way, so when you mod it out, you get G mod gamma, and that's the fundamental group of that is exactly gamma. So if we think of the elements of gamma n as elements of the fundamental group as loops, so the conjugates of them are exactly like shifts of the loop. And saying that this converges to identity, it means that there are a lot of non-trivial loops, because gamma n is not trivial, that by shifting them we in a sense, they converge to shrinking and shrinking, like they converge to be a trivial loop. Of course, they're never a trivial loop. This means you have something in the manifold that goes in more narrow and more narrow.
Yeah.
So you're not compact.
Think of that picture of the pseudosphere from last time. You know, we described that surface of revolution, the tractrix, which goes like this. You can have
Yeah.
you have many loops to just keep shrinking.
So yeah. So maybe this is the picture that there is some you escape to infinity if you're not shrinks.
Just to mention, such a thing is called the cusp.
Because
When you say such a thing, you mean not exactly that, but anything that like.
Well, I prefer not to give a formal definition of a cusp, but you think of this, as you mentioned, you think of this if and only if criterion for non-uniformity of a lattice as an algebraic formulation of what cusp means.
yeah, and I'll give an example which might relate to it. So let's return to SL2Z and SL2R. So SL2Z and SL2R. Now let's get some Gn, let's get some gamma n such that this converges to 1. So let's define example. Define Gn to be an inverse in the diagonal and gamma n to be identically u, which is 1, 1, 1. So if I'm not wrong, Gn u Gn inverse is precisely 1, 1, 1 over n squared. You can check me. Up to some, maybe switch the rows, I don't know. So this definitely, when n goes to infinity, this approaches the identity matrix. N goes to infinity. And this is, well, definitely this is in SL2Z without the identity element. So by the previous criterion, we get that the image of Gn in SL2Z, right? The image of Gn? Yes, sorry. Yes? The image of Gn escapes to infinity. And n goes to infinity. So, SL2Z is non-uniform. It's non-uniform in SL2R. And it seems actually that this example is fundamental in a way. And I'll say what I mean by it. There's some claim that says for a semi-simple algebraic group with a unipotent element, I'll write it down. It's better this way. Let's suppose G is semi-simple P group with a unipotent element U, which is different than 1, where U is in gamma, a lattice. Then G mod gamma is not compact. And the reason why is using this example. Why? The outline, there is a lemma which says that there exists a phi homomorphism from SL to R to G such that this is called Jacobson-Morozov.
Very useful.
Yeah. Especially to this remark, such that phi of 1, 1, 1 is exactly U. So it takes the unipotent in SL2Z to U, and now we can denote Gn to be phi of this guy Gn, and inverse N. Now what happens if we do Gn U Gn inverse? Because phi is a homomorphism, we have phi of that matrix over there, 1 over n squared, 1. And phi, okay, phi is continuous. So this goes to phi of the identity, which is the identity. And by the previous corollary, we get that G mod gamma is non-compact. And I think that's what I wanted to show. Maybe someone has something interesting to say.
Yes, I should be someone. Just one remark here is that this corollary is actually an if and only if. So given a semi-simple liquid, a lattice in it will be not compact if and only if it has a unipotent element. But the other side is harder to prove. And also I want to make the remark that was mentioned here already that indeed in semi-simple groups we do have always both co-compact and non-compact lattices. And we have plenty of them, and most of them come from some arithmetic constructions as SLN Z does.
Alright. I guess now we're waiting for the food.
I think waiting will not help. So thank you for the lecture. And I guess someone should follow.